Hi everyone, welcome to the High Energy Seminar. Today our first speaker is Kelley. Luke is a sixth-year graduate student at Harvard University, and he got his bachelor's degree from University of California, Santa Cruz. And his research has been focused on high-energy transients, short-lived astronomical phenomena. And today he's going to talk to us about massive black hole binary mergers and their gravitational waves.
Thank you. Hi, great to be here. I'm visiting all the way from P Building, so it's nice to be out here. Visit the CFA is great. Thanks to everybody for coming, so I'm really excited to talk here. It's actually my first time talking at the head group. Probably shouldn't have waited this long, but great to be here. So overall, I've worked on lots of different types of transients over my grad student and before that career, but now I'm pretty locked in on massive black hole binaries and the low frequency gravitational waves that they emit and how to observe them. So I am a theorist, I'm sorry, but I think this stuff is really interesting, and it has like a really rich wealth of observational consequences, and things that I'm really excited about are coming up in the next few years. I think this is a great time to be thinking about this regime. So just a basic outline, I'll give you the background of the gravitational wave background. That's what people are usually talking about when they're talking about low frequency gravitational waves from massive black holes, as opposed to LIGO-like sources, which are short-lived transients from stellar mass black holes. I'll talk a little bit about pulsar timing arrays, which are the mechanisms by which we think we can detect these, how you actually make detections, what that looks like, and then a few of the kind of other directly electromagnetic observable sides of that. So the basic idea is, instead of using a laser interferometer, ground-based laser interferometer like LIGO, you can use the nature's accurate timers, pulsars, distant pulsars, spread around the galaxy, and you can correlate the deviations from their times of arrival and use that to measure perturbations to the space-time metric, just the same way that you would with a laser interferometer, just using natural sources. So what you're sensitive to here is based on your total observing baseline, so something like 10 years or so, and then the interval in between your observations, which just determines your Nyquist frequency. So that's something like 10 observations per year. So you have a nice range, 2 decades of here in time. And you're sensitive to sources based on the RMS noise in your times of arrival, which is usually something like microseconds, if you're very lucky, maybe tens of nanoseconds or so. So this is showing the residuals of pulsar times of arrival. Green and blue are just 2 different instruments here. And the residuals, average residuals, are down here, microsecond scale or so. So if you compare those microsecond residuals with the characteristic duration of gravitational waves, which are year scales, you get down to sensitivities of about 10 to the minus 15 in terms of gravitational wave strain. So that's a very modest 6 orders of magnitude less sensitive than LIGO is, but that should be roughly good enough. So the types of sources in this regime are low frequency, fairly wide binaries of massive black holes, so millions to billions of solar masses. Here I'm showing binary separation versus the gravitational wave frequency that they're emitting, and the color is the different masses here. And it turns out that you're most sensitive to the highest mass black hole binaries in this regime. So we're really looking at the stuff kind of up here, and again, this is our frequency observing band that we're looking at. So it's massive black hole binaries at separations of 10 to the minus 3 to 10 to the minus 1 or so parsecs or so. So still fairly wide separations. The first thing we should ask is there actually anything in this parameter space to observe? It seems like a natural question to ask yourself. Well, we know that there's a very high occupation fraction of massive black holes in galaxies. Near all or all massive galaxies have massive black holes. We also know that it's a natural part of their life cycle for massive black holes to merge. That's how, for massive galaxies to merge. That's how they grow. So presumably, yes, there are at least circumstances by which 2 massive black holes could come together. Now, if we wanted to calculate prospects for a background, the process was outlined a number of years ago, mostly by Stirl-Finney in 2001, and the idea is basically the same as the Sultan argument for AGN. So the idea is you integrate up the total energy emitted in gravitational waves over cosmological time, over redshift, and that tells you the current day strain in the universe once you redshift that signal. So for that, you need some sort of black hole population, which just goes into your evolving number density distribution. And if you plug in purely gravitational wave-driven evolution, so the binaries harden together by gravitational wave emission, then you get this characteristic power law evolution, this f to the minus 2/3 spectrum in the strain. And the normalization is, not coincidentally, about 10 to the minus 15 or so. So this is kind of the canonical picture of the gravitational wave spectrum. The way you construct that population, the black hole population, has classically been using some Press-Schechter formalism, abundance matching, M-sigma type relationships. So you use the observed population of galaxies, you extrapolate to black holes, you assume that every galaxy merger corresponds to a massive black hole merger, and then you can generate the spectrum from that. Our take on this is to use hydrodynamic simulations. So I'm working with Lars Ernquist. We have the Illustris simulations, and these are simulations based on the moving grid hydrodynamic code called a REPO, developed by Volker Springel. And these are pieced together with smooth particle hydrodynamics to represent stars, dark matter, and black holes, and go into cosmological boxes where you evolve all of these particles over cosmological time. You put in prescriptions for star formation, for feedback, for black hole evolution, for metallicity, stuff happening, really cool, exciting stuff. And you get something like this. So this is showing one of the most massive galaxies evolving over time in this simulation box. And a big part of this evolution is these large-scale mergers between different galaxies. So what I do is I go into the Illustris simulation, I identify whenever two of these black holes come together, and those are my kind of merger events, my binary sources, and I figure out what their masses are, redshift distributions, and the extra benefit we have is that we have very accurate galactic environments for these systems also. So we know exactly the gas, dark matter, and stellar distributions that are surrounding these black holes as they're coming together. These simulations do pretty well. So this is a mock HST deep field on one side and the actual HST deep field on the other side. I'm sure you guys have seen this 100 times. I think the one on the left is the real one. This one's Illustris. Yeah, because we have diffraction peaks here. We should really put those in our simulated one too, and you really couldn't tell. So there are important differences when you do this kind of co-evolved version. So in Illustris, we have the black holes evolving with the galaxies in our simulations. If you use semi-analytic models or abundance matching, you have a very different type of pattern. So what I'm showing here are merger rates for galaxies. This is based on semi-analytic models. The merger rate as a function of redshift, and the different lines are different mass bins. So on the right side is Illustris. You'll see that these are basically showing kind of opposite characteristics. There's a huge variance based on mass and very little redshift evolution here, whereas Illustris sees the opposite thing. The mass bin, the colors, have almost no power on the merger rate, but there's a huge redshift evolution. So you do get very different results just based on these two different methods of analyzing the population. Of course, your end result, things like the M-sigma relationship or the quasar luminosity function, both methods are calibrated to work out for those. But as soon as you start looking at more complicated measures, they differ. So in the canonical calculation of the gravitational wave background, all of the interesting stuff is kind of glanced over in this distribution of sources. But if we use the Illustris results and do the exact same thing, we can still place our prediction in the same parameter space. So all of these colored lines are showing the canonical predictions for the gravitational wave background spectrum. So that's strain versus gravitational wave frequency. And this is the minus 2/3 characteristic power law. All of the points here are current upper limits from pulsar timing arrays. So these pulsar timing arrays are already cutting out good portions of this parameter space, and some people have been getting excited about that. So in this kind of simplistic calculation, if we put the illustrious results in, that's this black line, it's fairly consistent with all of the existing predictions, and it's just below the current upper limit. So that's promising. It's encouraging. And often these are measured by the strain at 1 year. So people usually quote that number. For us, it's 7 times 10 to the minus 16, and kind of the fiducial value overall models is about 10 to the minus 15. So right in the same regime. So people have been getting excited about this. They're saying that, oh, okay, we haven't observed anything, so now we can start to constrain things like cosmology, like the M-sigma relationship, and that is a very exciting prospect, but it's glancing over this huge issue of getting the black holes from galaxy scales on kiloparsecs down to where they're emitting gravitational waves at only thousands of AU scales or so. So this is a huge span, many orders of magnitude that you have to cross. So the assumption of this model is that all black hole binaries effectively cross that divide and reach the gravitational wave emitting regime. They do that quickly so that cosmological time isn't an important factor in that equation. And then once they get to the gravitational wave regime, once you get to those small separations, this formalism assumes purely gravitational wave driven evolution. So there's actually a conflict there. To get from the largest scales down to the smallest scales, you need environmental factors, things like dynamical friction, stellar slingshots to dissipate energy, gas drag. You need these mechanisms to get to the smaller separations. But then once you're there, this is assuming that those are negligible, and gravitational wave emission is the only thing carrying out energy, and you use that assumption to calculate this power law background. Actually, it's more complicated. So just expanding this equation into another way of phrasing it, where we're still integrating over the entire population of binaries over cosmological time, and here we're just expressing this as the strain from each source, each black hole binary instead. And in this kind of carries some of the important assumptions here. So there's a term for the sources in the past light cone, and then there's also something called the residence time or the hardening time. So this is just how long each binary spends in each frequency bin emitting gravitational waves. So if you have something like stellar scattering coming in that brings these binaries closer together faster, they have less time to emit gravitational waves, you attenuate the gravitational wave spectrum and you decrease it. So in actuality, the merger scales are gigayears. So taking into account this past light cone, how long it takes binaries to get to small separations is very important. Some of the binaries stall. They don't come to the gravitational wave emitting regime at all. And finally, once they get there, these environmental factors are still at play. You decrease that residence time and you attenuate the gravitational wave signal in the pulsar timing array band. So in particular, there are four classes of factors that mediate the hardening process. The first three are typically classified as environmental, so dynamical friction from gas, usually on the largest scales. Stellar scattering, so you have an intervening star comes in and extracts some energy from the system, usually on parsec scales. The final parsec problem comes from these scales. Sometimes you'll have a viscous disk, so you have some gas drag in there also. And then finally, on the smallest scales, gravitational waves take over. And remember that I said the PTA sensitive band was roughly between about 10 to the minus 1 and 10 to the minus 3 parsecs. So that's not just gravitational waves, but also a viscous disk and lost cone scattering that's important on those scales. So some of these factors have been explored recently, especially in the last 5 years or so. And so far, every previous paper has used one mechanism or another together. So they usually still assume that all black holes come together effectively, and then they implement one of these mechanisms on top of gravitational wave emission. With the illustrious simulations, I've implemented all of these at the same time. So instead of assuming that black holes come together effectively, we start out with them at kiloparsec scales, and we actually integrate their evolution ahead using these mechanisms to see which ones come together effectively. So we start out with more accurate merger rates based on the illustrious simulations. We use these more detailed environments that are properly correlated with the black hole populations. We include all of the hardening mechanisms for their evolution. We do assume circular orbits for the moment. And this is all self-consistently derived. So the resulting picture looks something like this. This is hardening timescale in years versus binary separation in parsecs. Each color is a different hardening mechanism, and there's kind of a dark shaded region here with a black line. That's the cumulative rate of hardening. So red is dynamical friction, which is important on the largest size scales. Blue is loss cone scattering, which is actually fairly constant across different separations. Finally, viscous drag in the yellow region and gravitational waves in green. The inset panel shows which mechanism is dominant for most binaries. So like I was just saying, dynamical friction, stellar scattering, viscous disk, and gravitational waves. Gravitational waves only become dominant at very small separations. This region comes in a little bit further if you only consider the most massive systems which contribute predominantly to the gravitational wave background. But still, this is a very complicated landscape, and the characteristic timescales are gigayears. So those lifetimes are very long, and a lot of these most massive systems aren't assembled until low redshifts. So this is just showing the lifetime between the two black hole particles coming close together within a galaxy or so, and them actually coalescing. And this is mass ratio versus total mass of the system. And you can see that the lifetimes are typically very long, Hubble times. They only become even gigayear timescales when you get to both high mass ratios and high total masses up in this top right corner. And that means that the fraction of systems which actually coalesce before redshift 0 ends up being pretty small. So again, it's only the high total mass and high mass ratio systems where the coalescing fraction approaches unity, and still it's usually closer to a fraction of that or so. And if you're either low mass or low mass ratio, then you actually have a very small chance of merging. So you could just have stalled binaries out there, stalled black holes. So this is kind of for our fiducial model, which is fairly conservative. I think it's very realistic, but it's not overly optimistic. If we switch to a case where the stellar scattering is extremely effective, so the loss cone is full, as people say, then the lifetimes do get shorter, and the coalescing fractions do get larger. So this softens it to be that if you're either high mass or high mass ratio, then you'll probably merge pretty effectively. But even in this case, there are still a lot of stragglers at low masses and mass ratios that should still be stalled. Okay, but what does this mean for gravitational waves? The environmental effects have a significant effect on the gravitational wave background. So this is the detailed gravitational wave background taking these effects into account. So the previous spectrum I showed is this blue dashed line. So that's ignoring all of the environmental factors, assuming that all black holes come together effectively and merge purely due to gravitational waves. The realistic calculation is this red line here. So it's decreased in amplitude by about a factor of 2, and there's this very strong spectral turnover at lower frequencies. And this maps directly into the environment that processes these. So at these lower frequencies, larger separations, things like stellar scattering and gaseous drag are more important, and they cause the stronger attenuation. And you can see that even at the highest frequencies, there's a slight spectral deviation in the slope because of these factors. So the amplitude is down by about a factor of 2, and the spectral shape tells you something about the environment directly. So in particular, I can show this is the same hardening plot, so hardening time now versus frequency here, and I've tried to line them up correctly. And you can see that gravitational waves take over only in about this region predominantly, and the viscous disk, the circumbinary disk drag, is still important on all larger scales. So one example of how you can kind of directly back out information about the environment from the gravitational wave spectrum is if you think about the loss cone, so the stars that are scattering with the binary. When you place a massive black hole binary in a cusp or a core of stars, it starts scattering them out, and you deplete the loss cone. So in that case, your loss cone would become empty. Now, you eventually reach some sort of steady state where stars are scattered back in diffusively, or maybe there are processes like triaxiality or third perturbers that very effectively refill the loss cone, and that's called a full loss cone. So what these different lines here are showing is just if you interpolate between these two regimes, what effect that has on the gravitational wave background. And I've chosen to show the loss cone scattering because that's one of the biggest questions in black hole evolution, is how effectively is this loss cone refilled? So as you adjust this parameter, which interpolates between these two regimes, not only does the amplitude vary considerably, but the turnover changes shape and changes location. So by making an actual measurement of what this shape looks like, you can directly map that into environmental hardening mechanisms at different separations corresponding to each frequency bin. So if you're trying to constrain something like galaxy merger rates, the M-sigma relation, or merger fractions, those end up being fairly degenerate because they only affect the amplitude of the gravitational wave spectrum. So that's possible, but it's somewhat hard to do. What really tells you more is the full spectral shape of this, and that maps directly to the environment. It can tell you about what kind of gas or circumbinary disk is around there. It tells you about what the stellar density profile is, if there's a core, if there's a cusp, if the loss cone is effectively refilled, etc. But how do you actually make a detection? So the power laws I was showing before are somewhat overly simplistic. Actually, you need to consider that binaries are not a continuous fluid, which the equation I showed below kind of assumes, and you need to take into account that they have finite numbers. So you can't have a quarter of a binary contributing to your gravitational wave background. And you also have to think about your Nyquist sampling of frequency space with pulsar timing arrays. So if you do that, you get something that actually looks much more like this. So the power law spectra I'm showing now in these purple lines here, and a more realistic sampling of the universe is shown in the jagged line. So there are, I think, 10 different realizations here, with one of them highlighted in blue. And this is just taking into account different Poisson statistics, so different realizations of the light cone to get you this variance. It might be a little hard to see, but I'm also highlighting certain bins in teal here. And those are bins in which a single binary is dominating the gravitational wave power. So more than, I think, 90% of the gravitational wave energy in those bins is coming from a single source, and that's called a continuous wave source. So the first thing you'll notice is that this kind of turns over at higher frequencies and it gets much steeper, and that's because of these finite number effects. There are very few sources at these higher frequencies, and that's also why you tend to see more single sources in the higher frequency ranges. And this has been seen before. Alberto Cezanna has studied this extensively, of why that turns over the way it does. But it is very encouraging that we might see these individual sources, and you could identify them and study them in particular, maybe even see how they evolve in frequency over time. So if I change these from individual realizations to contours, it looks something like this. And again, this is the most recent upper limit. So that upper limit is actually only at the 2 sigma or so level from our predictions. So it really wouldn't have been outlandish if there had already been a detection or so. And that should make us very optimistic that we could make a detection very soon. In particular, if instead of using our fiducial evolution models, you use very pessimistic models, then this only goes down by about a factor of 2 or so, which is surprisingly modest, at least surprisingly to me. So I'm starting to do the calculation of, as you observe for longer and longer periods of time, as you beat down the noise and increase your signal, what is the probable time to actually making a detection? And that's still in a preliminary phase right now, but it really looks like 10 years is somewhat pessimistic for when this should happen. So this is just a simulation of different realizations of the universe for longer and longer baselines of observation using a mock pulsar timing array, and it seems very promising. And the prospects for actually detecting individual sources are pretty high as well. Now, what if you don't make a detection? That's actually not a terrible thing either. And the reason is that while if you lower the gravitational wave background, you're decreasing the fraction of systems that coalesce. But that means that you're increasing the number of systems which don't coalesce, or increasing the persisting fraction. And the persisting systems should occasionally be observable as dual AGN. So if you lose out on the gravitational wave side, you should win on the dual AGN, offset AGN side of things. So this is just an example of the closest observed dual AGN system known, separation of about 7 parsecs or so. Just to show that in a different way, as our gravitational wave observations get better and better, we're kind of forcing these lines further and further down. So we're decreasing the coalescence rate, the merger rates of these systems. But at the same time, if we improve our statistics on the dual AGN population, we can insist that this line has to be at a certain height or higher. So we're very close to a point where these are going to collide, and hopefully that's where science happens. So this is something that I'm really excited about. I think this is a very unique situation in which we can't really lose. Either you detect gravitational waves or you detect large numbers of dual AGN systems. And I think people need to just go in and very carefully do these dual AGN statistics to see what fractions of systems are actually out there, what fractions are explicitly not out there, and then we can actually make this comparison. So with that, I'll leave you with my conclusions. Thanks. Yeah.
Is there any indication from the experiment you've run here what separation these will get?
Yeah, there seems to be a kind of bimodal distribution. So there tends to be pileups at about kiloparsecs or so at the very high mass ratio systems. So you might have a billion solar mass black hole and then a million solar mass black hole that's stuck at a kiloparsec or so. Maybe it'll have a small bound stellar core to it, but that could easily be hard to observe. There's another pileup at about a parsec or so, and that's the classical final parsec problem. And those tend to be basically any mass ratios, but tend to be lower total masses. So there should be a good spread of things. One of the follow-up projects we're doing is kind of calculating that very explicitly, trying to fold in the local gas environments to see what predictions we can make for their accretion rates, so we can make concrete predictions to compare to. So I think that's one of the biggest things that needs to be looked at further.
Did you look into whether there's any accompanying X-rays or gravitational wave heat?
Yeah, so that's something that people are really excited about, especially Zoltan Hyman at Columbia and Andrew McFadden are looking at this. That's not something that I've looked at all, but the big question there is you expect to open a gap in the disk, and the question is, does that gap persist after they coalesce so that you're not accreting and you don't observe something, or does it get filled in? So it's another interesting question that's being looked at. I hear the story now is that there should be continued emission throughout the process and perhaps a slight brightening soon afterwards. It should be on the viscous timescale of the disk nearby, so months, weeks to a year, I guess. Observable timescale.
Any other questions? If not, let's thank Luke.
Stole this. Oh, right.
Is this on?
Our second speaker today is Dr. Dan Schwartz, and Dan is a senior astrophysicist in the Center for Astrophysics, and he got his PhD from the University of California, San Diego. to talk to us about the kinetic flux of X-ray jets and the supermassive channel.
Okay, thank you. A group of us carried out a survey of about 54 quasars that were strong radio sources, flat spectrum radio sources, relatively bright, and which had radio jets extended at least 2 arc seconds so that we could resolve the X-ray jets with Chandra. We actually detected 31 of them. In this talk, I'm going to tell you how we use the X-ray observations to derive the amount of power being carried in those jets, and then I'm going to try to connect that power to the physics and numerics of what's going on at the supermassive black hole where these jets originate. Okay, so why do we care about the jet power? The power in the jets is a significant fraction of the black hole energy budget. It indicates the available energy which may be available in other channels. For example, winds, the ultra-fast outflows that we heard about at last Tuesday's talk. It's very hard to estimate the total energy in winds or outflows because you don't know the exact sizes and therefore the exact amount of mass that's outflowing. You measure the velocity and column density very well. But heuristically, from the fact that jets, we're going to find out, can have essentially the Eddington accretion luminosity. We can intuitively think that maybe winds and outflows have that amount of energy available to them. The power in the jets is comparable to or greater than the black hole radiative luminosity. I'll show you that in a slide later. This supports calculations and simulations that are done of super Eddington accretion onto black holes. It solves the problem of the very rapid growth of black holes to masses of 10 to the 9th solar mass at redshifts of 6, which is only 1 billion years in the age of the universe. The power of the jets is a crucial ingredient of feedback. It interacts with galaxies, with clusters of galaxies, and it was known from very early on in Chandra observations that in fact the amount of energy emitted by jets can solve the cooling flow catastrophe problem in clusters of galaxies, which Einstein first, the Einstein satellite that is, not the person, first revealed. And it's revealed by seeing that these bubbles here are filled with radioplasma, so you can deduce how much work the radioplasma had to do to inflate those bubbles, because you know the temperature and density of the surrounding gas, and you measure the size of the bubbles from the image because of Chandra's exquisite angular resolution. So jet power is important. Why are X-rays important? Well, only in X-rays are we directly measuring the power in kiloparsec scale jets by observing the jet. All other estimates depend on the effect that the jet has on an external medium, such as the bubbles or extended radio lobes. So it's nice to know that by looking at the jets, they actually do carry enough power as inferred by other indirect observations and scaling. And of course, putting all those together is important. Now, to estimate the power of the jets, we have to understand what's emitting the X-rays and the radio. Very early on, we noticed that for almost all jets, for substantial regions along the jet, the shape of the X-ray and radio profiles are virtually identical, within a factor of 2. The X-rays are the green crosses here, the radios, the smooth red lines. The radio jets typically do extend past the end of the X-ray jets. I'll get back to that later, but that makes sense. The very close agreement of the profiles implies that the X-rays and the radio both originate from a common population of relativistic electrons. We know the radio emission is synchrotron because we measure polarization. The most natural explanation is that the X-rays are an extension of that synchrotron spectrum up from the Lorentz factors 10 to the 4, 10 to the 5 that are emitting radio waves, up to 10 to the 7, 10 to the 8 that would emit X-rays, notwithstanding that the lifetimes of those X-rays would be of order 100 years or less. And many people like that explanation, but it's wrong. It's wrong because we can measure radio and X-ray directly in many jets, many regions of virtually all the jets, and they just don't connect because there's optical measurements or upper limits that prohibit that. So the X-rays in general are not an extension of the radio emitting synchrotron spectrum. There are exceptions where such an extension can be allowed. So the emission mechanism is almost certainly inverse Compton scattering. The X-rays are produced by relativistic electrons scattering on the photons of the cosmic microwave background. And how does that work? Well, the observed radio synchrotron emission relates the magnetic field strength in the jet to the particle density in the jet, but in a combination that you can't separate. For a power law distribution of relativistic electrons, which you can tell from measuring the spectral index of, well, you actually measure the spectral index of the radiation and relate it to the index of the electrons. You can separate the magnetic field and electron density normalization by assuming minimum energy. The derivative with respect to the magnetic field setting equal to 0, where the minimum energy in turn of relativistic where the total energy of relativistic particles is related to the magnetic field via the synchrotron radiation. So this has been used in radio astronomy for 50 years. But in the case of relativistic jets, there's some new wrinkles. A relativistic jet will have an apparent Doppler factor depending on the Boak-Lorentz factor of the jet and its angle to our line of sight. When you do all the proper transformations, you get an expression for the minimum energy magnetic field in the rest frame of the jet. And you can use the Felton and Morrison inverse Compton formulas to give a combination of the Doppler factor and the Boak-Lorentz factor. It's known that the ratio of the radio to X-ray flux densities when extrapolated to a common frequency is just the ratio of the energy densities, b squared over 8 pi, to the energy density of the cosmic microwave background. Now here's where we get a big win because we know the properties of the cosmic microwave background. We know that the energy density depends on the temperature to the 4th power. The temperature is enhanced by 1 plus z. So we get a big enhancement from the redshift effect to the 1 plus z to the 4th power. From a homework problem in Jackson, if Jackson's still used in E&M courses, I don't know, you know that the apparent density in a medium moving with a Boak-Lorentz factor of gamma is enhanced by gamma squared. So we have a large enhancement of the cosmic microwave background density, and that's what essentially lets us see the X-rays that from the lower energy electrons. So we have our unknowns of the magnetic field and delta, gamma, beta, but we only have 3 equations, so we still have to finesse something. And what's usually done is to assume that the Lorentz factor equals the Doppler factor. And that's not quite as ad hoc as it seems because for any given Doppler factor, it puts the jet angle at the largest angle to our line of sight that it could have. So it's the largest solid angle in which we could have found it. Also, it gives the mean value of the Doppler factor since its maximum value asymptotically for a very large gamma and a jet exactly in our line of sight is only 2 times gamma. So it's intuitively okay. I'm also going to show results, though, where we simply acknowledge that we don't know the angle of the line of sight, and we just treat it as an unknown parameter and look at a run of possible results. Okay, so now we're ready to calculate the power. The power is also variously called kinetic flux, kinetic energy flux. What we really want to know is the enthalpy flux. The enthalpy is the ability to do work on an external medium, and that's what is important for feedback and for observations of how jets interact with external media, probably how black holes grow in concert with the mass of the bulge of the galaxy that they're in. So the enthalpy flux is just the internal enthalpy density in the rest frame of the jet. So for the relativistic particles, 4/3 the energy of the particle, plus the Poynting flux. Now, in these jets, we're seeing the radiation from electrons, or electrons and positrons. But the jets are probably electrically neutral, so they must have either protons or positrons to make that neutrality. In the case of protons, we need to subtract off the rest mass because we can't realize that energy. The protons won't annihilate. In the case of positrons, they will annihilate. We can use that energy. Then so the internal enthalpy gets multiplied by the cross-sectional area, the velocity, which is essentially the speed of light, and enhanced by the gamma squared to give a formula for the power of the jet, where this factor K2 is 1 for positrons, 1830 for protons. And the X-ray observations allow us to estimate the magnetic field and the Bulk-Lorentz factor, modulo the caveats I mentioned about the degeneracy in the Doppler factor. So here are the results when we assume that the Doppler factor and Bulk-Lorentz factor are equal. The what I call orange, but you probably call yellow or gray histograms represent the case where protons provide the charge neutrality. The blue or gray histograms are the case where positrons are providing the charge neutrality. The only quantity for which it really makes much difference is the enthalpy flux, where proton jets are something like 8 to 10 times 10 to the 46 ergs per second. Positron jets are probably a factor of 5 or 6 lower at something like 1/2 to 2 times 10 to the 46 ergs per second. But we get, in both cases, more or less, Doppler Lorentz factors in the range 6 to 12, magnetic field strengths in the rest frame of the jet 10 to 20 microgauss. From the deduced angles to the line of sight, we get the lengths of the jets, and mostly in the range 1 to 400 kiloparsecs. That's the length of the X-ray jet. As I mentioned before, the radio jet does extend a little further, and that would be reasonable in terms of the fact that as the jets slow down, the Lorentz factors decrease, you won't have the enhancement of the X-rays. Also, we see many jets that bend, so bending also will decrease the Doppler factor because the bends are almost certainly away from the line of sight since the jets are also close to the line of sight. So let's just take a look at saying we don't know the angle to the line of sight and parameterizing all the results as a function of the unknown angle to the line of sight. So each solid line here represents the power of one of the particular 31 jets that we detect as a function of any angle to the line of sight. The triangles are the point where the Doppler factor equals the Lorentz factor for each jet. Now, this assumption cannot be correct for any one jet. It can't be exactly the same. But if we think about the collection of all jets, if systematically they were all really at much smaller solid angles, there's two issues. One is the number of parent populations would be exploding, getting very large. Also, there'd be no reason not to detect the ones at much larger solid angles, where in that case much larger is still only 4 to 5 degrees. Conversely, if systematically the whole population was really at much larger angles to the line of sight, we'd be getting powers of 10 to the 48, 10 to the 49 ergs per second, which some people might think is an absurd amount of power. I don't know if it is or isn't. But in addition, at much larger angles to the line of sight, your Doppler factor would start decreasing toward 1. You get this larger power because the Lorentz factor has to become larger at larger angles to the line of sight, but the Doppler factor is going to go down to 1. If the Doppler factor is 1, the jet you're not going to see a one-sided jet. You're going to see a two-sided jet, because we see one-sided jets not only because they're enhanced coming toward us, but they're also diminished going away from us. So we've got these numbers. Then for our collection, we're going to consider this as the Doppler factor equals Lorentz factor result as the power of the given jet. So here's what I mentioned before. We look at the power of the jet, the green crosses, against the radiative luminosity of each of the quasars. This blue solid line is the case of protons providing charge neutrality, and the jets by and large have more power than is radiated in the optical. The red dashed line gives a case where positrons provide charge neutrality. In that case, they're spread more equally around the line, but it's comparable or greater than the radiative luminosity. The two graphs on the right show for protons or for positrons how much power as a function of the black hole mass. The black hole mass is taken using a fundamental plane argument with a formula from Gultekin et al. And of course, it's a very crude estimate, but the solid blue dots give the power of the jet. The solid line here is the Eddington luminosity, and the dashed line is the 10th Eddington luminosity. So for proton jets, we've got a substantial amount of power, 10% to 50%, say, of the Eddington luminosity. For positron jets, a factor of 5 to 6 less. The green crosses are the radiative luminosities, and the red triangles are the X-ray luminosities of each of the quasar cores. So where does this power come from? Well, it's got to come from the supermassive black hole. If we take a fiducial amount of time of 10 million years and multiply it by the power of the jets, we get a certain amount of total energy. We divide it by c squared, and we get an equivalent amount of mass that had to be converted to energy to produce that power. And that's the blue dots here shown on this scale, the minimum amount of mass. This scale is the actual black hole mass estimate of each object. Now, for a maximally spinning black hole, which are shown as these orange or yellow, if you will, squares, you can retrieve 29% of the energy. In other words, the total mass of a maximally spinning black hole is 1.4 times the irreducible mass. So if we divide our required minimum masses by 0.29, that gives the position of each of the squares in this diagram. And they're way below the actual mass line of the black hole, which is this solid line. So that's a very viable mechanism. In fact, even if the black hole's spin parameter is only 0.2, 20% of maximum, in that case, you can only recover 1% of the mass energy of the black hole. Only 1% is in the rotational energy. So these points are 100 times the mass points, but they're still allowed. They're still comfortable, or they're still below the line which represents the actual total mass of the black hole. So what's the mechanism for launching these jets? There's lots of discussion in the literature these days of magnetically arrested disks. The accretion flow advects in magnetic field until the magnetic field becomes so strong that it stops the accretion flow, it balances the gravity. And for a maximally spinning black hole then, these magnetic field lines are going to be wound up into a kind of a spiral, and the observations of rotation measure gradients, which Gabouste and her colleagues have done, in fact, directional rotation measure gradients, really supports that picture of the helical magnetic field. So I'm going to just assume that at some initial point in the jet is purely Poynting flux, purely electromagnetic energy. So the Poynting flux then we can equate to the power that we see in the jet at 100 kiloparsecs. It's got to be at least that big. And this is just crudely taking a cylinder of radius r, which depends on the sign of the plane of the magnetic field to the spin axis of the jet. But now the jet is taking not only the energy from the black hole, it's also taking its angular momentum. So you have to conserve the angular momentum as well. And we crudely take, well, that as just the radius of the same cylinder across to the momentum flux in the Poynting vector. And by another Jackson homework problem, you know that the angular momentum flux is the energy divided by the frequency of the circularly polarized wave, which is presumably or taken to be the frequency of the black hole rotation. So we have relations that involve the magnetic field and the distance as a function of the angle of the magnetic field to the plane of the average plane of the magnetic field, because it's spinning around, to the spin axis of the jet. And we can use these to construct the structure of the inner jet. So we've got the radius here in orange. This is the magnetic field for one particular actual jet in the sample. It's 20,000 Gauss. And as the radius increases, the magnetic field has to decrease. It's expanding. So this is the cross-sectional structure of the jet, which unfortunately I don't know how to tie to the longitudinal structure of the jet. But the one thing you can say is that it must occur well before any kind of recollimation shock. It has to occur well before particle accelerations, because I'm assuming all the energy is in the magnetic field at this stage. Okay, so we can use this and we can calculate the magnetic field right at the gravitational radius of the maximally spinning black hole. We can calculate the flux, the magnetic flux then that's threading the black hole. So we had the magnetic field and we have the gravitational radius from the mass of each black hole. And these are the points plotted here. On this axis, we're plotting the saturated flux, which comes out of simulations of magnetically arrested disks. And this factor 50 can vary somewhat. It's 50 times the square root of what's essentially the accretion luminosity. So our agreement, which would be the solid blue line, is off by a factor of 3 or so. That's probably excellent agreement. It probably supports the plausibility of this picture of the origin of a jet. After all, the magnetic fields that we're estimating at the black hole are really the minimum fields, because some other energy may be lost by the time they get out to 100 kiloparsecs. And conversely, I've assumed Eddington Eddington accretion rate for the mass loss here, and that can be less as well. Of course, I've got to say that the opposite arguments also apply. So, you know, these points can move in various directions across this map. So the jet power, when we interpret the emission as inverse Compton off the cosmic microwave background, it can be supplied by the rotational energy of even moderately spinning black holes. If we assume that it initially starts out as a pure Poynting flux from the magnetic field threading the black hole, then the jet power requirements at 100 kiloparsecs imply a magnetic field energy density which is comparable to the Eddington accretion density and comparable to the saturated flux predicted from magnetically arrested disk accretion. And this is, I think, the first kind of observational connection supporting those results which come out of simulations. Thank you.
There are jets. There must be accretion which holds the magnetic field on the black hole. If there is accretion, there are also optical and UV photons. What makes the CMB photons more effectively upscattered than the optical and UV photons?
Okay. The CMB photons I'm talking about, to make the X-ray jets that we observe are at scales of kiloparsecs to hundreds of kiloparsecs away from the quasar. They're not at the quasar core. And the CMB field is stronger at those kinds of distances.
Dan, are there any local analogs to these ones, like 3C273 or any of the local? Is it just that these appear this way because the CMB is so much more dense than high redshift? These energies, the jet energies, seem to be very large. I'm just curious if there are any essentially local to redshift Q10s analogies or analogs to these sources.
Well, the dearth, if you will, of local quote-unquote relativistic jets is the same as the dearth of the Faranoff-Riley 2 sources. That they're just a lower density in the universe and they aren't in the nearby universe. The 3C273 in particular is not this kind of jet. We know that because its profile nowhere, the X-ray and radio profiles nowhere match each other. The X-ray jet energy is much less compared to the 3C273 quasar X-ray density. So, and there's direct observations of optical spectral shape that show that it is synchrotron.
That there basically is no local analog and that this is essentially due to AGN evolution.
The
A larger number of these more powerful ones at high redshift than just what it is. Is that the conclusion?
I don't know of anything closer than something like 0.6, but I do not conclude that that's because of the enhancement due to the cosmic background at higher redshifts.
Have you totally ruled out synchrotron self-Compton?
Synchrotron self-Compton is ruled out because the sizes aren't small enough for the synchrotron photon, the radio synchrotron photon densities to be dense enough.